All right, welcome to the lesson on washer method. So we're going to break this up into 2 different days, 2 different videos. So we're going to have 2 examples in this one, and then we'll deal with some of the harder washer problems later on in the week. The first thing I want to talk about is if you took a circle and you found the area of the circle, and you continued taking the same circle with the same area, and you stack them all on top of each other, that's going to create a cylinder. So we have a cylinder like this, okay? So how would I find the area of the cylinder? So think back to geometry. First thing we need to know is how to find area of a circle. So we should all know that that is going to be pi r squared. And if I'm taking the same circle, stacking it on top of each other over a certain height, that's how I find volume of the cylinder. So volume of the cylinder is going to be pi r squared times the height. Okay, so let's keep that in mind. So the same idea is if I have a washer. So a washer, if you've ever built anything with nuts and bolts, it's good to have a washer in there. So what a washer is a circle with a small circle inside. And then we have this area here that's made out of typically metal, sometimes rubber. But we have this area. So how would we find the area of this washer? The actual area of the metal or the rubber? Well, we would have this outside. Let's make it green. How do I, if this were all filled in, all this was filled in with green, how would I find area of that? That's just a circle. We already talked about that. We would deal with pi r squared. Well, we could still do that. We could say pi r squared, but I don't want this middle piece. I don't want this stuff in the middle. So what would we do? Well, we have a red circle here. We have this little tiny circle, and we want to find the area of the interior, which is just pi r squared again for that inside circle, and we would want to subtract them from each other. And we could simplify this to be, actually let me switch. If we took the pi out of both of these, we could say that it's pi times the difference of the 2 radius squareds. Okay? And then we think about a cylinder. What if I made a cylinder with a washer? So here's a washer. Actually, we'll make that the top. So there's a washer. Okay? And if I stacked a bunch of washers on top of the same washer, on top of each other at a certain height, we would have this again. So we would have this interior, and then okay, so what we're trying to find is we're trying to find the volume of this cylinder made from washers. Okay, so we would do the same thing. We'd take area of the outside piece, and then minus the area of the inside and multiply it by the height. So this is where our formula comes in. So our formula for our washer method, if you remember from last year, it's the integral of pi times big R squared minus little r squared times dx. So this big R squared is the outside radius, or the outside area, and then the little r squared is the inside radius. So we took those away from each other to find the difference. Multiplied it by pi, and then we multiplied it by the height. So this height is represented by the change in x. So this infinitely small height, and it's changing every time, okay? And that's going to be determined by our boundaries of our integral. So let's go ahead and take a look. I know it's kind of hard to picture, but we'll go through these. I'll make some more videos. So the first problem. So I have two functions, x squared, and I have square root of x. So if we look at that on a graph, this is what it looks like. And we're going to go ahead and rotate it around the x-axis. So the big radius, or the outside radius, so it's the thing furthest away from the axis that we're rotating around, which in this case is our x-axis. So that distance is greater than this distance. Okay. So the outside radius is going to be determined by our height of the function, the red function. And then the inside radius, the little radius, is going to be this blue function. Okay? That's how we determine the y value of the function is going to be the radius. So we have x squared and x squared. So this is our x squared right here. We have our square root of x right here. Okay, so let's set up our integral. So integral from something to something, so we'll talk about that here in a second. So big radius, so that's the outside radius, so that's going to be our square root of x. And remember, it's radius squared minus our little radius, or the inside radius, which is x squared. And we have to square that. And we have our height, dx. And now we need to talk about the boundaries. So the boundaries are going to be the intersections. So it's the same thing we talked about with area between two curves. It's finding the intersection points and talking about what the x values of those intersection points are. So we have a 0 right here and a 1 right here. So we're going from 0 to 1 for our integral. Now the pi that's in the equation from the pi r squared, that's a constant, so we can just go ahead and we can pull that out front. Okay, so we don't have to write it twice or even write it outside and have more parentheses. We just pull it out. Okay, so now we can go ahead and we can evaluate our integral. So taking the antiderivative of this, the first thing you typically want to do is clean it up. It makes the integration a little easier. So if we squared the square root, that's just going to cancel out. We get x, and then square square, that's x to the fourth. Now we integrate. So the integral of x squared over 2 minus x to the fifth over 5. Evaluate from 0 to 1. Okay, and then remember that constant's out front, so we're just going to leave it out there. So now if we plug in 1 and then we plug in 0 and subtract the values, we'll find the volume of the solid that we created by rotating around the x-axis. So plugging 1 in gives us 1/2 minus 1/5. If we plug 0 in, we can see that those just cancel out. So we'll have this times pi. So 1/2 minus 1/5, so that would be 5/10, and this would be 2/10. So 5/10 minus 2/10 is 3/10 times pi would be 3 pi over 10. So that's the volume of the solid of these two functions rotated around the axis. Okay? So now let's take a look at rotating those same two functions, but this time we're going to go around the y. We're going here. So if we look at that, if I look at our graph here and we're going and we're rotating, around the y-axis, now what the further function is this red function. The x squared function is further away from the y-axis than the root x. So notice the blue line is shorter than the red line. Okay, so red line's our big radius, and then the blue line is our little radius. So we got to keep that in order. Okay. And it might be helpful to write down what your big R and your little r. So let's say big R is, so big R of x, it's a function. We said in that case was the x squared. And then our little r is our root x. You don't have to write the x, but it is a function. But you could just write a big R and a little r there. So now we are rotating around the y-axis. So it's very important to note that when you're rotating around the y-axis, you need to be in terms of y. So we're going to solve these equations and put them in terms of y. So if we solved for x here, that would be square root of y. And this one's going to be y squared. Okay? So now, when we do our integral, we're doing the same thing. We're doing the integral, pi on the outside. So something to something, we gotta figure that out. And then big R squared minus little r squared. So we're in terms of y. So if we're in terms of y, well, let's look back at the graph. Actually, I'll just go to this other graph, it's a little bit better. So if we look at the graph, and we're in terms of y, we need to be on the y-axis as well with our boundaries. So we know the two intersection points already, but if we go all the way across, we're going from 0 to 1, okay? It's the same boundaries as last time, but it is the y, and sometimes it will change depending on what the two functions are, so be careful. So from 0 to 1, we're doing the same boundaries. 0 to 1. Okay, so if we clean this up, I mean, some of us can see that it's pretty much the same thing we had last time. No, that's not squared. That's just y minus y to the fourth. So if you go ahead and you roll through the integral again, you find the antiderivative, and then you evaluate with 1 and 0, you should end up with 3 pi over 10 once again. So it's kind of a coincidence that this happened, because sometimes, I mean, just depends on the function. Sometimes this does happen where it's the same thing around the y and the x. A lot of the times it's going to be two different values though. So make sure if you're asked to do both, because most of the time it will not be the same answer. And that's going to wrap up the video. Like I said, I will post another video later in the week to work out when we are off the y-axis and the x-axis. So try the work and let me know if you have any questions.